Hey guys, this is Professor Janacek, and I want to talk about some special trigonometric limits, and then we'll also look at some examples of taking derivatives with trigonometric functions. First off, we have a couple of special limits here. The limit as x approaches 0 of sine x over x. Now you'll notice that as x approaches 0, sine x over x becomes undefined. However, it turns out that this limit, as x gets close to 0, not when x is equal to 0, but as x approaches 0, we actually get close to 1 on this particular function. Similarly, as x approaches 0, the cosine of x minus 1 over x, again, at 0, this is undefined, but as we get close to 0, it does approach 0. Now, I'm not going to prove these, but they are nice limits to have down. So again, those functions are not defined at 0. You can see that because 0 is in the x is in the denominator, so 0 would be in the denominator. So not defined there, but we do have limits there. We can use these for a couple of examples. Let's take a look at example 1 here. The limit as x approaches 0 of sine of 4x over x. Now this does look a lot like what we have for that first special limit, but we have x and x. X for the argument of sine, x in the denominator. Here I have 4x as the argument of sine, but only an x in the denominator. And we can't just go putting a 4 in the denominator. That doesn't work. But what we can do, because I do want to get that 4 in the denominator, what we can do is just multiply a 4 in both the numerator and denominator. Alright, so that gets me the 4 in the denominator like I need. Now we also have a property of limits that says if we're taking the limit of a constant times a function, it's the same thing as the constant times the limit of that function. So I can write that 4 as a coefficient in front of my limit. There we go. And now, according to our rule, if this guy is the same as this guy, the argument of sine is the same as the denominator, which is what I have, 4x as the argument of sine, 4x in the denominator, then in that case we get 1. Of course, there's still that 4 out in the front, and so this one simplifies to 4. Okay, not so bad. Let's take a look now, example 2. Things get a little more complicated. We're taking the limit as x approaches 0 of sine of 3x over the sine of 5x. All right, so here we have two different arguments. Cannot put them together, but let's see, what can we do? Well, it's true that I can multiply this sine of 3x over sine of 5x. I can multiply this by 1 and it doesn't change anything. I just need to figure out what's the precise form of 1 I want, and I want 1 over x over 1 over x. Again, doesn't change anything because I'm multiplying by 1 here. So what we end up with is the limit as x approaches 0 of sine of 3x over x over the sine of 5x over x. Turns out in this situation we have the limit of a quotient, right? This is a quotient in here. And so the limit of a quotient is the quotient of those limits. So I can take the limit of sine of 3x over x over the limit as x approaches 0 of sine of 5x over x, over x. And now that each of those, the numerator and the denominator, look very much like example 1 here. So in the numerator, I will multiply that by a 1, and that gives us 3 sine of 3x over 3x. Notice the 1 there is 3 over 3. In the denominator, I'm going to multiply by 5 over 5. Okay, and so 5 over 5 is the special form of 1 that we're using. And now, of course, in the numerator, I'll factor out, or I'll write that constant, or that coefficient of 3. In the denominator, it's 5 That is my coefficient. And now here we are. I've got the limit of sine of 3x over 3x. Again, those bits need to be the same in order for this to work. But now that they are, we have 3 times 1 in the numerator, 3 times 5 in the denominator. Oops. How about 5 times 1 in the denominator? Where is my head? So we end up with 3/5. All right, not so bad. Let's change the gears just a bit. Let us try to find the derivative of y is equal to the sine of x minus x times the cosine of x. Okay, so y prime, what do we get? Well, the derivative of sine of x is cosine of x minus, now here you'll notice this guy, that is a product, x times cosine of x, which means we need to use the product rule. Product rule says we take the derivative of the first thing, well, the derivative of x is 1 times the second plus the first times the derivative of the second. We can simplify this just a bit. We have cosine of x and let's see, watch that negative. I've got a negative out here. I also end up having a negative in there. So watch those positives and negatives. We end up with negative cosine of x plus x times the sine of x. Of course, you can see there that we can combine a couple of those. We get y prime is x sine of x. There you go for that one. All right, let's try example 4. We've got y is equal to 1 plus sine of x over 1 minus sine of x. So y prime, again using the quotient rule, we're going to take the derivative of the numerator, that's cosine, times the denominator, minus the numerator, times the derivative of the denominator. All of this is over the denominator squared. Well, let's see, what do we get here? Multiply some things out, we get cosine of x minus sine x times cosine x minus, now watch this, be careful, I've got a negative here and a negative here. I'm going to go ahead and distribute both those negatives along with that cosine x there in the back. Again, watch those positives and negatives, so we end up with plus cosine x plus sine x cosine x. In the denominator, we have 1 minus sine x quantity squared still, and you can see now we've got a couple things in the numerator that will combine, and in one case they end up giving us 0. So combining things in the numerator, we end up with 2 cosine x over 1 minus sine x quantity squared, and that is y prime. All right, one more example. Let's see if we can find the derivative of e to the 2x times cosine x. Now this time we're going to use the product rule. So we're going to start by taking the derivative of the first. Now remember, for the derivative of e to the 2x, we end up with e to the 2x, right, e to that power, times the derivative of whatever is in that exponent. So we end up with e to the 2x times the derivative of 2x is 2, which of course is 2e to the 2x. All right, so that was the derivative of the first part, 2e to the 2x times the second plus, now we're going to take the first as is, times the derivative of the second, that's negative sine. So we end up with 2e to the 2x cosine x minus e to the 2x sine x. It is common practice to go ahead and factor out that e if we can, and I see we have e to the 2x in both cases. So, that's supposed to be a y prime there. Y prime is e to the 2x times 2 cosine x minus sine x. And there you go. Enjoy!